All right, so measurements, an introduction, that's what we've been doing. So, in overview, theoretical foundations for about 5 lectures, signals for about, I guess it was like 6 lectures, where we did things like Fourier Series, transform, sampling, sampling theory, aliasing, reconstruction, discrete Fourier transforms, measurement systems as dynamic systems, so dynamic system representations, 0 with first and second order system measurements, or measurement systems, another second order measurement systems. Well, that'll be interesting to see when we get there, what that's about. And then transient response characteristics, also twice. I don't know if there's like 2 parts to this. I think that's what it is. Yes. I don't know. Then properties of Lti systems, response to periodic inputs, phase linearity. Remember we did some homework over that, where we did the decoding stuff. That was fun. And then we did prob and stats forever. It was like 4 weeks, I think, that we spent on prob and stats. And then uncertainty analysis, and a little bit of electricity measurement, and we didn't really get to the other ones. So, but you guys have a good foundation. Unfortunately, I didn't get a chance to get to all that I wanted to, but yeah. So let's just walk through.
All the ones that are titled measurement.
Yeah. Well, it's what it is these would be I mean, they are measurement, but I would say they'd be more like instrumentation, I guess. What devices you actually use. Yeah. No, whatever. Strain measurement. You guys will figure those out.
We'll figure it out in systems.
Sure. We'll say that. So, remember we started with like, what the hell are we doing when we measure things? Quality, quantity, magnitude, and scale. Remember how numbers were maybe like actually just counting things, measuring things? So some people thought that. It's kind of cool. I tried to assault your conception of realism, and we kind of came like in these lectures. I mean, we sort of talked about some like fundamental concepts and fundamental quantities, fundamental ways of going about doing measurement and thinking about measurement. We went through a bunch of different theories, but I think that in the end, kind of the thing that we kind of came down to was that there is a circularity in what we're doing, because we have to have a conception of what it is we're going to measure before we can measure it, but we have to measure it before we have a conception of it. So like it's just a sort of like circularity that continues to move forward, however. So I mean, we talked about like how the concepts of mass have changed over time, length, those concepts have changed, and yet it's not like it was worthless to study them before we had the current conception either.
By
So.
the way, I found out why the rod changed. They found out about normal force.
Okay.
So in finding out more about normal force, the way that they had set up, it would bend,
Huh.
which would be a problem.
Interesting. Yeah. Was that another class that you found that out in?
And I just looked it up last night because I was listening to all of your lectures.
Oh, cool.
Some didn't make it up.
Nice. Yeah, they're good for like, Saturday mornings.
No, it was Sunday evening.
I don't think I've seen a Saturday morning in like a year.
Oh, man.
I'm up at 6:30. Doesn't matter.
So we called it a non-vicious circle, and how learning from history is useful and that type of thing. And then we started talking about math-based stuff, and everybody breathed a sigh of relief. So we talked about signals first, and signals are so fundamental to measurement because that's what our measurement looks like, a signal. No matter what you're measuring, they all end up looking like a signal. So we talked about different types of signals that are common to measurement theory. So sinusoidal signals, decibels. We talked about the fundamental difference between periodic and aperiodic signals, right? Ramp and sawtooth functions, triangle functions, square waves. And then we started talking about Fourier series. And remember that Fourier analysis is all about thinking about a signal in terms of the frequency domain, right? So we have the time domain and the frequency domain. The frequency domain comes down to what are the frequency components that comprise the signal. So a sinusoid, a pure sinusoid, has just one frequency component, but a function that has multiple frequencies of sinusoid and multiple amplitudes for those different frequencies could have multiple components. And a function that is periodic has a Fourier series representation, which is essentially a representation of that function as a sum of a bunch of sinusoids at different frequencies and different amplitudes. And your function's amplitude and frequency content is called the spectrum, right? The spectrum of that signal. And we can do things like plot that. So we define the Fourier series. There's the cosine, or the trigonometric format of it. And then there's the complex form. We talked about harmonics as being, so whenever you have a function that's periodic, its frequency spectrum shows up at discrete multiples of the fundamental frequency, right? There's no content in between those fundamental frequency components. So the multiples of the fundamental frequency. So for instance, the square wave that was up here, its fundamental frequency is, in terms of hertz, is 1 over t. And there's a frequency component at integer multiples of 1 over t in frequency, higher and higher, but there are no lower frequency components than that. That's the lowest frequency. It's the fundamental frequency. Okay, and that's just what the Fourier series is. It's just a sum of a bunch of these frequency components at different frequencies. And then you can convert between the trigonometric and the complex forms. This was a graph that was trying to get us used to thinking about a signal in both domains. So in the time domain, which goes this direction, we might have a square wave or something that looks kind of like a square wave. And we think of it in the frequency domain, in this other dimension, as having an amplitude and a frequency associated with each of them, and that they're just all summed up to create this signal. So when we do what's called Fourier analysis, we're breaking down a time domain signal into its frequency components. And we do Fourier synthesis, we're summing them up to the time domain signal. So, yeah. We found out how to compute the Fourier series components, which was fun. And then we started talking about Fourier transforms. And for signals that are aperiodic, there is no Fourier transform or Fourier series representation. However, there is a Fourier transform representation, which instead of just having frequency components at discrete frequencies, the transform has components in the entire spectrum, in the entire frequency domain. So you can have a component at any frequency, not just multiples of the fundamental, which opens up the door a little bit to representing what we call transient functions, or functions that are aperiodic. So we did this discussion that was essentially a derivation of the Fourier transform from the Fourier series. So we started the Fourier series, something that we felt like we understood. Well, I felt like I understood it. I don't know about you guys. Aaron understood it.
Oh, yeah.
Yeah. And then we slowly derive the Fourier transform from that. So sort of like as a limiting case, like as you take the limit, as you make your frequency components closer and closer together in the limit, you get this spectrum, this continuous frequency spectrum. And this is the result of that, the sort of limiting case in the example we were doing. Then I finally define the transform in the trigonometric form, and I give the complex form of it as well, which is more common to see than the trigonometric form of the Fourier transform. It's more common to see the complex form. And then I mentioned, there's a lot of stuff you can do with this. Thinking about it in terms of, thinking about a signal in terms of the frequency domain is by far the most important thing in my mind of the Fourier transform, the Fourier series. However, you can use them to solve differential equations. So that's another aspect. But you can also use the Laplace transform, which is something you guys have used before to solve differential equations. And since the Laplace transform applies to more types of systems, a lot of transient systems, we tend to use it a lot more than the Fourier transform to solve differential equations. But you can use the Fourier to solve differential equations. It's very similar to the Laplace transform. Okay, then we talked about sampling. And we talked about the mathematics of sampling first, the Dirac function, how to represent a signal that's sampled. Had that pretty graph that took me forever, I remember. It was fun. And the spectrum of the sampled signal we could compute. And then we stumbled upon this sampling theorem where, well, we're getting close. We saw that it duplicates itself when you sample. And that led us to this sampling theorem, which said that you have to sample at a frequency greater than twice the max frequency of a component in the signal, or you're going to get aliasing. It's not that you're only going to capture part of the signal. It's that you're going to think you're capturing something that's not there, and that's the really dangerous part about aliasing, is that it looks like there's a signal there. Just like as if it was a real signal. You can't distinguish it. So fundamentally, if we're measuring something, we don't know what its frequency components are in it. We kind of are in trouble because, which is, in a lot of cases, we don't necessarily know for sure all that's in it, right? So we could be seeing something that's not there if we don't know about some frequency component at some higher frequency, which is a bummer. So what do we do? How do we get around that if we're running into this aliasing situation? What I was showing in this was that you can't tell. I have the color coding here to tell you which one is associated with which period. So the blue one is supposed to go with the blue one, but without the blue color coding, you wouldn't be able to tell the difference between these two signals. And that's the problem with aliasing, is that you just can't tell if it's aliased or not. So how can we be careful and avoid aliasing? Besides increasing the sample rate as high as we can, which is what we typically will do. We'll try to sample pretty high if we can. We can filter, and we want to filter before or after we sample. Yeah.
I just chose the opposite of what he did. Just chose one.
Yeah. So if you sample first and you get the alias in there, you're already toast. Like the air right now that we're trying to breathe. You can't de-alias it. It's already aliased and you're screwed. So you have to filter before you sample. So the idea is that at high frequencies we can get the filter to take stuff out. Remember the magnitude spectrum. So if we looked at the magnitude spectrum, you guys remember that?
I don't do.
This is the multiplying factor that the system has for any input at a given frequency. So usually at low frequencies, there's some DC pass through. So sometimes it's just 1. Other times it's some non-unity factor. And then depending on the system, I mean, you might have a resonance, whatever might happen. But if you have a filter, then hopefully it drops off, and then it usually will level out then at some point. So, or maybe it'll drop off indefinitely. So this is like a multiplicative factor, and then usually this is on a log scale, so it never quite reaches 0. It looks negative here, but it's actually just not. This is still positive. This is just more positive. So,
Which is not mathematical.
yeah. This is like 0.1, and this is like 100. Okay. So we have at higher frequency, this would be like a low pass filter, which is what you would want before you take your samples, because the signal that comes through at these lower frequencies is all that's all going to pass through. It's going to get multiplied by this number. Maybe that number's 1. 1's a common number to multiply it by, but it could have some non-unity factor as well. And then when you get to these higher frequency stuff, it gets filtered down. And the amplitude might be like, like 0.00001 out here. Maybe there's some frequency component in the signal that you're measuring that comes in up there, like right there, and it would get aliased down, right? And that would be bad. It would look like, so maybe your sample rate is like here. It would look like it's showing up right here. That would be bad. But since its amplitude is going to be scaled down so much from this low pass filter, it'll show up still. It'll just be really small, except for there were 2 of those. It'll just be really small, so it won't matter as much.
So essentially, it's almost like there's a mathematical function statistics where you can take the outside percentage of some percentage on the outside of your sample, like 10% on either side of it, remove it.
Mm-hmm.
But this is just like incorporating it, but scaling it down, so we're not actually removing it, we're just making it more useful, I guess.
Yeah, I mean, ideally we could remove it, but our filter can only do so much.
Oh, I see.
And so we try to make it as small as we can. So our filter, an ideal filter would come out here to whatever frequency we think our max frequency that matters is. Probably we would only want to come out here to like half of what our max frequency is for our sampling rate. And then we would want to just make this thing just drop off to 0 if possible. So that anything coming in above that would just be gone. But we can't build filters that are perfect like that. What we do is we build filters that are, they drop off at some rate, and then stuff that's way out here gets very much filtered out, but stuff in here gets filtered, but not as much. Stuff in here doesn't get filtered much at all, and then it all passes through with these low frequencies. So that's what this, this aliasing thing, what we try to do is we try to use these filters. The very simplest type of filter you can use is just an RC circuit. You can just use it. That's just a first order low pass filter, and you run it through there. If you're in the lab, then you did a rectifier circuit with the diodes. So you took an AC signal and you turned it into a DC signal. And that DC signal came out like super choppy, like this, right? But it was all positive, so its mean value was a positive value. And then you put it through an RC filter, which it didn't exactly make it flat, but it just made those components a lot smaller, and what was left over was your ripple. So that was an RC filter. I mean, better and better filters would make that thing cleaner and cleaner looking coming out. So
Quick question, obviously,
Yeah.
can you make a filter that only filters out the low stuff? And
yes,
so you can reverse it. in the
yeah.
sense
So that would be a high pass filter. So it would just be the very opposite, and you can do that actually with an RC circuit as well. You just have to flip it.
You just make sure the capacitor goes first within the circuit, right?
Yeah.
Why don't you just hook it up to the resistor?
You can just hook your output to the resistor. Yeah.
It doesn't really matter the order that they're placed in the circuit.
It doesn't because it's in series.
Yeah.
But if you think of the output as being the one over here, then yeah, you'd switch them, and then the output would be the resistor.
So, Dr. Rico,
Yeah.
that H, is that different than the transfer function like we've just been talking about? Or
Yeah.
is that-
So H is the transfer function. We would typically say H of S is the transfer function. So in mechatronics, we just started talking about this recently, right? And H of J omega was what we defined in this class to be the frequency response function, which is the last system representation that we need to introduce, that we'll introduce in system dynamics for mechatronics. But for this class, we introduced it really briefly early on, and we just defined it to be, so remember how H of S is the ratio of Laplace transforms of the output over the input? This is also the ratio of the output over the input, but it's the ratio of the Fourier transform of the output over the Fourier transform of the input. So H of S is Laplace, but it's still a ratio of output to input. H of J omega is Fourier, but it's also the ratio of output over input. And the way to transform between these two, remember, so we did a chapter on this, and we can look through it in the notes, but essentially what it was you take S and you just substitute in J omega.
That's it, right? And you can go both ways.
And you can go the other way too. You just find your J omega, and you substitute in S. I know, it's pretty wild. Oh!
No.
Don't have it ready. I need to have like a shortcut that just like launches.
Strike F4.
So much to do, so little time. I'll spend my winter break working on that problem. Getting shortcut keys for cool gifts. That would be a great use of my winter break.
It's probably an F.
You stole it again.
Oh man. Okay, so if you're in the mechatronics class, which most of you are, my guess is that when you go back over the material in chapter 3, which is just around the corner, discrete Fourier transform was a Fourier transform, but for a sampled signal. That was the one where we decoded stuff. Blah, blah, blah. Yeah, so then we got to the measurement systems as a dynamic system. So if you're in mechatronics right now, probably if you went back through this chapter now, things would make a little bit more sense in connection to the mechatronics class, because we've now hit on most of these models. The only one that we haven't is the frequency response function, which is amazing, but we're not going to talk about it until next semester.
Forward to it.
Yeah.
Epic sarcasm.
Epic sarcasm. It's like you guys don't even know how awesome this stuff is. Like you're one day going to wake up with somebody asking you to do an analysis of something, and you're going to be like, oh no, how do I do this? And then you're going to be like, you know what I could do? I could represent the system as one of these system representations. I could represent it as a differential equation. I could put it into MATLAB and simulate it. I could represent it as a transfer function. I could do all kinds of stuff with that. I could represent it as a state space model. They'd be very impressed. Is that I can't really tell what's going on back there. Brianna has a question. Okay.
What percentage of the test is going to be like conceptual questions and then actual calculations?
You know, I don't have a good number for that. But I do feel like
With 95% confidence, it will be.
That is the exact face I pictured you having when you asked that question right there.
If we ask again the night before, will you have the test ready then?
No, not the night before, 2 a.m.
ask me as we get closer and I'll probably have a better idea. This test is going to be really hard for me to write. It's going to take me some time.
Us too.
Can you make it?
It's gonna be really hard for
Like
us to
the
study for.
mechatronics test we just got back today.
Yeah.
So
Can we actually have like that test again, but like different numbers?
The what? The what?
I saw the test that like they got back today, and I would
No
totally
thanks.
love to do that.
I'm good.
Right?
I'm
I'd
alright.
love to do something.
I would love.
Migrated measurements does not require
I would help
mechatronics to be
you.
involved
Don't worry.
with that.
It's
We'll
not
study
that-
with you, Aaron.
Anyway. I
Yeah.
feel like
You also have a question.
You said the word Dirac Delta a lot when you lectured about this the first time, but you skipped over it entirely.
We just get into chapter
We're
3.
just getting there.
Yeah. Oh, well, actually, no. So
Darn it.
it showed up back here, too, when we did sampling. So the Dirac Delta was used when we did sampling. So all those arrow things, these
Are
guys,
Dirac Delta.
those are Dirac Deltas.
Yeah, I remember.
So Dirac Delta,
They were talking about it.
yeah. A Dirac Delta,
How do you spell it? We don't know.
nobody knows. Nobody knows.
Direct.
Yeah.
TV. No.
It's Dirac Delta, right?
It's Dirac Delta.
Dirac?
It's Dirac.
Like Game of
We were
Thrones?
just
Like the
looking about
Dothraki?
Like
Dirac.
Dirac, but Dirac.
Dothraki Delta.
Dirac.
I'm gonna roll with Dothraki.
Dothraki Delta function, yes. So, yeah, Paul, I think it is, Paul Dirac, famous mathematician. He did all kinds of stuff. Actually, I'll draw it like this. So say the way that it's typically discussed is x. Well, I'll use t because most of the time we're thinking in terms of time, and
On your class.
it's true. And then we'll say this is the origin. Then the Dirac Delta function, you could think of it as being like, so I'll draw it as like a triangle at first. That's how it's often depicted. So it's 0 everywhere. I use a different color. It's 0, and then it hits there, and it goes up, and then it goes down, and then it goes to 0. So, a couple properties that it has. I define it in chapter 2 somewhere, I guess. But it's what you get if you keep moving these sides in closer and closer to the origin. It collapses completely down to have 0 width, okay? So it only has, it's 0 everywhere except for at time equals 0, okay? So delta of t for t not equal to 0 is 0. And it has actually an undefined height. We think of it as getting like peakier and peakier and peakier, and then its height at time equals 0 is actually undefined. So delta of t for t equals 0 is undefined.
So it's not infinite?
I mean, sometimes people say infinite. We like to often think of it as being kind of like infinite, but strictly speaking, it's undefined at that point.
Yeah,
Wait,
wait, do
0 to
something to the
0.
Dirac Delta function to move the sides in closer and closer?
Sorry?
Did we do something to the Dirac Delta function?
Oh, well, it's just what we're doing is conceptualizing the Dirac Delta function as being this sort of triangle where like we collapsed the sides in, and then it has this super big peak on it. You can just, this could be the definition of your Dirac Delta function if you wanted to. The other aspect, there's only one more aspect of the definition, and that is that the integral from negative infinity to positive infinity of the Dirac Delta function is equal to 1.
Makes sense.
So if you integrate over the whole thing, clearly the area is 0 for all of the time it's 0, right? So it gets all of its area at this little spike. That's where it gets all of it, yeah.
Is tau just the regular time constant?
Tau is just a dummy variable to integrate over here, because strictly speaking, we're integrating over time, and so we shouldn't really use t in there. You guys know. I don't know.
So
Brown, aren't you a math major
So
too?
the second T is actually a time,
No,
not a
but
tau.
wait,
It looks like you drew a tau for d tau.
It is tau. It's tau. It's
Tau
just
tau.
not the time constant tau. There's just too many damn things that are t.
But no, you could put t in there though, because you have limits.
Unfortunately, we do not have
Even though there are
time, so we
defined
should-
limits, you'd have to define
Yes,
those limits in the
it's
variable. So the dummy variable would
Man.
be
I knew that
the
something
tau
like that would
in
come
the
too.
integral, and tau would be infinity or negative infinity. Limits.
Cannot shake me.
We don't know. I don't know. You might be right. I'd have to think about it.
My calculator teacher was really anal about it.
Okay.
And she made a kid get up on a test because he forgot to put limit infinity.
Dang,
He dropped the top.
I would.
So, yeah. We don't know for sure. Nobody knows. Question mark.
Okay.
So,
Can we write that on the test?
yeah, sure. The idea though is that the area under this is 1.
So
And-
it's Gaussian?
So
Okay.
it is actually a distribution function, and so it can be used as a probability distribution function if you want to, because its area is 1.
Yeah.
Yeah,
Makes sense.
yeah, and but what we use it for, we use it for a couple different things. We use it to be a mathematical representation of sampling, and the way that we do that is that when we sample a function, we use the Dirac-Comb function, which is the sum of a bunch of these Dirac deltas, and we shift the deltas by some amount, like t. And that means that this thing is 0 everywhere except for at t, right? At which point t minus t is 0, and then delta has its spike. So we put one of those every time we're going to sample, and we stick it into an integral with our function. That's how we're tricky about it. Because it's not defined at that point unless you go through an integral, and then it has this thing called the sifting property, which we talked about. Sifting property. And when you evaluate, and I did not prepare specifically for this topic, so I may get a little bit of the notation wrong, but the concept is correct. If you have f,
My test.
yeah, right?
The numbers. might be
Fortunately, I'm not taking this
I
test.
did not prepare for this topic.
So
With 90.
f of t delta of t minus t dt, I believe is how it works. What you do is you stick in the delta function that's shifted to some time value, and you stick it in there with f, and this actually comes out in the remember, this makes f of t 0 everywhere. I mean, this multiplication, I guess, it doesn't make f of t 0. It makes this multiplication 0 everywhere except for at the point where t equals t. And then if you integrate over that point, what you get is f of t out, which is exactly a sample value. If you think about trying to sample a function, you want to know what its value is at some time t. You could stick it in with this, and it might seem like a long run for a short slide.
And then you write 4I equals 1 to n. That's
Yeah.
t I minus.
Totally.
And just run that through the whole thing.
I want to have you guys hand write MATLAB code. It's going to be great.
Be an expert shooting that.
So I won't have you hand write MATLAB code, I promise. So the idea, though, is that you can use this. It's this sifting property.
I'm so sorry.
This sifting property, you can use it to sample a function. Okay, and that was one use for it. The other use we use the Dirac Delta function for. So that was chapter 2 was the sifting thing. For chapter 3, the dynamic systems chapter, we use it as an input. So it can be also an input. Can be the Dirac Delta function. And that's one of the reasons that we call the Dirac Delta function the impulse function, is that we use it to model an impulse impact or something like that. With a mechanical system, we use it to model like a really sharp blow to the system, or if it's an electronic system, like a spike in like the voltage or the current, and see how the system responds to that. So it's a type of function that we use. It's a little bit like the step function, and in fact, you can. You might make mathematicians mad, but you guys know how the step function is 0 until time equals 0, and then it's 1? You guys remember that?
That is true.
Yeah.
Definitely.
If you take the derivative of this, it's 0, 0, 0, infinitely high spike, 0, 0, 0 afterwards. And so sometimes people think of the Dirac Delta function as being the time derivative of the unit step function.
Interesting. Cool.
So that's one way to conceptualize it as well. So we use it as a type of as a function to model a type of input to a system. So maybe for a measurement, you want to be able to detect like a spike that happens. So say you're maybe trying to detect an impact that's going on in your system, or maybe you want to detect like a power surge or something like that to shut something down. You would model your system, and then you would say, I wonder how it responds to one of these spikes. It also has a lot of interesting properties in terms of the frequency spectrum, because theoretically, a real Dirac Delta function, which in reality they all have some finite width and they're not infinitely peaky, but a real Dirac Delta, or like a theoretical Dirac Delta function, would have all frequency components in it. So you can actually characterize a system's entire frequency response technically by just bopping it with a hammer and then just measuring its response. Technically, that is one way to do it. And it is a way that people really do measure too, is they put in an impulse and then they measure the response. And they do a fast Fourier transform on that. So, pretty cool. Yeah, so there's all that good stuff. How do we get back up to chapter 2, guys? Jeez. It was the Dirac stuff. Okay. And we talked about the different system representations: input-output differential equations, transfer functions, block diagrams, frequency response functions, Gauss AF, Gauss. That's Gauss. Zero order measurement systems. We talked about how they're like not real, but they're fun to think about. Step responses of first order measurement systems with time constants. And what I did, which I didn't do in mechatronics class, you guys might have noticed, I just gave you guys the solutions to these functions, to these, because I just assumed that that's something, you know, that we know and just do, right? I didn't want to get into like all the solution aspects of solving differential equations. So I just said, oh, differential equation, and here's the solution. And then we talked about how first order systems respond, how they're characterized. Talked about the sinusoidal response as well. And we talked about the dynamic error, which is how different the magnitude of the frequency response function is from unity, which is to say, if you had an input at that frequency, how different would the output amplitude be from the input amplitude? And we looked at the transient and steady state responses and how we had this phase shift that happened. That was all fun. Second order responses, we have a couple new things. So we had the time constant in the first order system. Second order systems, we have the natural frequency and damping ratio that come in. So a little bit different. You can have a lot more happening. So we spent the first lecture talking about free response. So free response is what happens if you give a system some initial conditions and just let it go, right? See what happens. So we talked about that first. Different cases, damping, critically damped, underdamped, overdamped. These different things happen. If it's overdamped, it just oozes to the new value, or back to the original value. If it is underdamped, it oscillates. If it's critically damped, it just barely doesn't oscillate. We talked about cantilever beam detector. That was fun. And then we did forced response. So we'll look at the step response first. And then the sinusoidal response we looked at in steady state. Looked at it in terms of the frequency response. And we saw this possibility of having resonance occurring with a second order system at the natural frequency or near the natural frequency. We talked about transient response characteristics in general for a system. And then exact transient response characteristics in terms of time constants for first order systems and for second order systems in terms of zeta and omega n. Lots of good stuff there. Response to periodic inputs. So you put in a sinusoid, you get out a sinusoid. So if you put in a sum of sinusoids, you can use superposition to get out a sum of sinusoids, right? If it's a linear system, and that's what we're going to pretend everything is in this class. And then we looked at, this was a fun one. You have an input spectrum. It goes through the system that has this frequency response function, magnitude, and we get out the product of them, right? So you take each one, take the product of that times that, you get that. You take the product of that times that, you get that. Product of 0 times 1.2, you get 0. That's the easy one.
Sure.
Yeah, that was the softball right there. You're supposed to smash that one. I did. I mean, it's way easier when you throw it yourself.
It's true.
Dr.
McConaughey, a quick question.
Yeah.
About formatting of the test.
Mm-hmm.
Because there's a lot of material here that's just very tricky.
Yes.
So is it going to be a similar setup to mechatronics exams, or just open note?
Yeah, I might even give you guys open book because there's a lot of reference stuff on this. I don't know. I always feel like I'm trying to make the decision that's best for you guys because I know if I give you too much material, sometimes people get lost in the material they brought and they never quite actually write anything on their test.
I mean, it's just that, for example, like if I were to use some of the homework problems for my notes, or just things that I've picked up along the way, which it's not as much as it probably should be, but is it going to be at least a few sheets of notes? I mean, I'm just curious.
Yeah. I mean, you can. It's open notes. Open notes for sure.
Okay.
If you guys want to do open book, I'm fine with that.
Double blind study. Half the class gets books. Half the class doesn't.
Do you guys want? raise of hands, who wants the book? I mean, you know, your expectations change slightly when you have the book material too, right? So are people, and also realize that some people don't buy hard copies of the book, and so it might be hard for them to bring in the book. So is there a strong sense of wanting to have the book? Not really.
Yeah,
Okay.
because
I'm pretty good with the notes.
I
Okay,
feel
yeah.
like if we have the notes,
Well, what? I
if
mean,
we want something out of the book, we can go ahead and put it in our notes.
Yeah,
And
I
with
think
the book
that
that you have,
we'll stick to the notes.
yeah, I mean,
So-
it's better not to have the book.
Now, democracy does not rule here. One person who wants the book deserves the chance for all of us to have the book.
I vote
This
that
is-
if you
this
want
is
the book, you can bring the
That's
book.
your messed up sense of the game of survival for these classes. Survivor.
I think we should set up like a contest of some sort.
It also makes a test on the 20th instead of the 15th. One person
Each side
matters.
put forth a champion.
One person matters, right?
I knew this was going.
Okay. I really think we probably are not going to use the book just because I think it's going to create more problems than it's going to solve.
Are you gonna
Yeah.
provide tables then? Like,
So T and Z tables will be provided.
okay.
If there are any other tables that you would like besides T and Z, let me know from the book or whatever. Let me know and I can try to provide
that one
those.
table from that one book that has like the solution to all the differential equations. What was that about?
I don't. You aren't going to need any solutions to differential equations that aren't in the notes.
Oh,
So
okay, I see.
yeah, because I gave you the first and second order ones. You're probably not going to need any other ones in that. I mean, this isn't a class on differential equations.
And then we could put them in our
So-
notes, just like bring in like a printout of like Laplace transform solutions and.
Yeah. So don't bring in like printouts of solutions. So I want you to bring in your notes, the notes that I provided for the class, your worked homework. Not even I don't even want you to bring the solutions to the homework that I provide you. Like if you have your own handwritten solutions or whatever you typed them, fine. But I don't want you to bring in solutions because I've seen people sit there and copy solutions onto tests, and I'm like, this is not the idea. This really wasn't the plan. This was not why you took a class here. This isn't why I taught you things, for you to sit there and copy a solution. I just want to like take that paper and burn it.
Don't you make up all your
Give it to your
problems anyways?
Yeah.
So when
I know, sometimes they're like, just like, well, here's a square hole. Let's just try a round peg. Maybe it'll work.
Yeah, if your round peg is
Scientists.
small enough, it'll fit.
And like,
Maybe.
I think that when I catch somebody who's like clearly just copying a solution that is not the right problem, but they're like, well, it looks like I'm doing something if I copy a solution, I give like negative points.
Do you give it to your dog?
Yeah,
Did you?
it's too. No, my dog doesn't deserve that. So, yeah, I wouldn't want to subject my dog to that. So and remember also, so if you have a periodic input, and you put it in to a first or second order or any order system that's not zero order, you're going to remember how the phase changes at different frequencies. So you're going to get phase distortion if your bandwidth isn't large enough to incorporate most of that signal. And so this was an example where we put in a square wave and we got out this thing, this orange thing. There was some definite distortion happening there. And so that was all of that. And then you guys had your exam, nailed it, no problem. And then we did prob and stats. Prob and stats. And this was fun. Aren't you guys glad that we didn't get through all the rest of the topics? We would have 400 pages worth of notes by the end of this. But no, there's still, there's lots more to
2
learn.
hours worth of tasks.
Conditional probability, Bayesian stuff. Ooh, remember true positives, false negatives, smiley faces, frownies. And then this with that stupid wiggle that I spent a lot of time trying to get rid of and it wouldn't go away. Remember Bayesian inference where there's like the a priori knowledge of something happened? Like for instance, if it's a test for something that is very rare, it's a lot harder to make a test that's accurate or that's going to give you good results because it's already really rare. So there's not a very good chance that you have it. And so, for instance, if it's a disease, but we found out horribly that cancer is super common. So
What was it, 50%?
that sucked. It was like, yeah,
But it could be a rare form of cancer.
that's true. So if you get a test for a rare form of cancer, the likelihood is lower that you actually have it. But once you get a second test and it's independent and it's also positive, then you're screwed.
How do you know it's over there if you touch
It's hard to tell.
it?
So different distributions. So,
I've never even seen that graph.
oh, you should have been here, man. It was so fun.
Why was I not here?
Yeah.
I don't know.
When did this
I
happen?
didn't see that.
Yeah, no, none of us saw that.
Nobody saw that graph.
Oh, you did. You know what it was?
Do you revamp a graph?
We were doing it in the notebook, and so this was like the compilation of the cases that we tried. So this was like,
Oh, that was the day we were in the MATLAB computer thing.
yeah, it was one of the computer ones.
Is it 14 pages of notes? Because if it is, then yeah, it was that day.
Yeah, 5 pages.
Oh, so no, that wasn't it.
Expectation, central moments, variance, taking sample means. So this, I would say 411, very important lecture because we introduced sample mean and we introduced sample variance and sample standard deviation and population standard deviation. Sample statistics as random variables. So then we started talking about like the mean of the means and the standard deviation of the means and the mean of the standard deviations and all that. And then we talked about how to estimate the standard deviation of the means from a single standard deviation. If this sort of thing doesn't show up on the final exam, then I really messed up. So this kind of thing, we did a lot of this, right?
How to produce a fake sample.
Yeah, so standard deviation of the means is how our uncertainty is computed for a mean. So remember that it all starts with our confidence interval, and then so our confidence interval ties back to the standard deviation of the means. So most of our measurements are our means that we're measuring, right? So we want to know how confident we are in that mean. Our confidence in a mean has to do with standard deviation of the means and not the sample standard deviation. So if you have just a single sample, then you can estimate what the standard deviation of the means would be. If you took a lot of samples and you took their means and then you computed the standard deviation of those, this is an estimate for that. So it's a really handy formula. So you can just take one sample and estimate what it would be if you took a lot of samples. It's pretty good. We talked about how to deal with non-stationary signals, which are signals that change with time, because we deal with that a lot. Like in your lab, when you guys measured those step responses with those motors, those were non-stationary signals. A lot of times in engineering, we care about non-stationary signals and not just like what one thing is, right? It's like, yeah, I measure that your speed right now is 50 miles per hour and then never care again afterwards. That's usually not what you want. Yeah, so lots more of that data stuff. Oh, I have the funnest idea for making something. How to do distributions, confidence intervals. We did Gaussian this time. So if something with a z-table doesn't show up, I will be surprised. Z-score. Look at that. That was fun. And then we did T, student confidence, student's T distribution. And remember, that's just like the Gaussian, but for smaller samples. It's a little bit better of an estimate.
And the table's backwards.
And the table's backwards. That's right. But actually, it's more like the z-table's kind of backwards for what we want. The t-table is more what we want usually. But you can use the tables to compute either one.
I think that's a trick question.
Maybe.
These tables, but the sample size is this. Which table do you use?
Oh, that is a good question. I should ask that. And I'll credit you, Aaron.
Aha!
And then multivariate, and we got correlation and covariance. Remember that? And then we're going to have these really pretty graphs soon. Oh, yeah. That was good. Regression. how to do regression. And then we got into uncertainty. And that all went back to, I mean, some of it came down to this RSS combination of uncertainties. But a lot of this came back to the confidence interval, right? And estimating our uncertainty based on a probability distribution from the confidence interval. So that was mainly what we did. That was what we did in the rigorous analysis here, combining the stuff that we know about it from the spec sheet and the stuff we know about it from the sample statistics that we measure. And then we just talked about electrical measurements, and that was a fun one. And then it was Friday, and we did measuring resistance well, and we learned about the Wheatstone bridge circuit. And we did a sensitivity analysis there, and talked about the null and the deflection methods. And that's all we did.
I have a question.
Yeah.
So,
Yeah.
how big are you on final number answers? Like,
I really like them.
if you asked us to calculate the uncertainty, and I like had an answer
I give lots of partial credit.
that was like the square root of this times the uncertainty in this plus the derivative of this times the uncertainty of this equals this thing, but I didn't find this thing.
Okay, there was a student on the mechatronics exam who screwed up one little thing. He forgot to write y equals, okay?
You gave me 64.
And yeah,
No, man.
but everything else in the mechatronics exam was correct. The inertia of that person getting right. I was like, we'll call it 100. We'll call it 100, you know? So that is where I like to be. That's the zone I like to be in, where I'm just like, oh, this is right, this is right, this is right. When you make me go looking in there and try to figure out where the hell you went wrong because your final answer is wrong, then I got to figure out why it's wrong. And then I got to put on my Hardy Boys hat, and I got to do all that, which is not my favorite thing. I like the inertia of just like going through and being like, check. So I do try to look for partial credit, and I try to see where you went wrong, but I only am willing to work as hard as you worked on the problem too. Like if you're just like randomly writing shit all over the page, I'm not gonna really like go searching for stuff. But if you like,
my entire college career right now.
but if you like, you know, try to organize it well and try to give me clues to like what you're working on, why you chose to do this, you know, whatever motivates stuff for me, explain things for me, then I'm going to try to follow it.
So what if instead of like writing out the actual numerical problem, we wrote out exactly how to solve it?
Yeah, I give credit for that. I mean, I do. I'm not going to give you like full credit for just explaining the process without doing it, but I would give you partial credit for knowing how it's done. And some questions that I ask are literally explain how you would do this.
It's gonna work. It's going to work.
And I would be prepared for that. So you might not have MATLAB or whatever, but I might ask you to explain how you would set up something to do this or that.
Like write down the MATLAB.
No, I won't ask you to write code, but I would maybe ask you to explain how you would do something.
In MATLAB.
I mean, maybe in MATLAB you could explain in broad terms. Like, for instance, I would take the mean of this. And then I would do, you know, like not like at the level of like what function you would use to do whatever.
It's not really like a MATLAB question though.
No.
That's more like what's your process?
Yeah, what's the process? And that's what I'm going to be asking. Like what's the process? It might be something that would require MATLAB to really do, like a regression, right?
Yeah.
You're not going to do a regression by hand of any magnitude. You might, yeah. I mean, I don't want to say you can't. I'm just saying probably not. All right.